My screen isn't going here. Start video. Okay, can people hear me out there?
Yes.
Oh, good. Okay. So the first thing I'd like to do is I'd like to actually go over some of the details of the final exam. I'll send you an email with these details and maybe some other things too. So I just want to kind of give you an idea what the final exam will be like, and I know it's a sort of different format from what we're accustomed to in this class. So the final exam for this class is a week from today. So December 11th, from 12 o'clock to 3 o'clock p.m. All right. And so what I'll do is I'll set up a Zoom meeting for this. So we'll set up a Zoom meeting. What I'll try to do is I'll try to have it be the same Zoom address as the actual class session. Okay. Now, for all for actually checking in, I suggest that you arrive to the final 30 minutes in advance, 20 to 30 minutes in advance. So I'll actually be there 30 minutes early. Okay. And make sure you bring your IDs. Fortunately, we've had some in-class tests, so I recognize at least most of the people by now. All right. Uh, the third rule is that camera should be on at all times. All right. That's just in terms of test monitoring and things. So unlike the midterms, this test will actually be an open notes and open book test. So you're allowed to bring notes, and it'll also be, you can also use the book, all right? And then you have a calculator that you can use. That's been true for the other tests too. And the only thing that you cannot use is you can't use the internet. So no internet use. Um, m- Part of the reason for not having the internet is I think it's very distracting. And so, and also it might cause your Zoom connection to crash too. So that's why I don't want any internet use during the test. But you're allowed to have your notes. You're allowed to have, use open book and a calculator too. Okay. Now, for actually doing things on the exam, you can actually write your exam on a tablet. Okay, and then send me, your exam back. So what I'll do is I'll actually send you the exam at around 12 noon to your email address, your UGA email address. And then, you can upload it onto your tablet. You could do the exam on the tablet. And then I'd like you to send the exam back to my email address. Okay. So you can use tablet or you can use paper. And then you have to scan your exam if you use paper, obviously. And then you're going to send your exam back to Nakano at uga.edu. Okay, so I'd like you to actually send your exam back so I don't lose it or you don't lose it or whatever. Okay. All right. As much as we can, the exam will actually end at 3 o'clock. And then, and also, you may want to leave the exam early. So if you want to leave the exam early, you should send me an email message or just send the exam to me earlier. Okay, so you can leave early. Send exam to me. And then you may want, so when you do that, I'll be monitoring my email throughout the exam. And once I actually get your exam, I can actually write you a private message in the chat saying that I received the exam. Okay. Are there any questions on the sort of general plan?
I have a quick question.
Sure.
So I've been using a PDF format of the book this whole semester.
Yeah.
Is that okay?
Yeah.
Okay.
Yeah, the PDF is fine. I don't know, you may want to have a different computer that you have the PDF on instead of your tablet.
Okay.
Right. I mean, you may want to have a laptop next to you and then you write on your iPad or whatever. That's fine. That's perfectly fine.
Okay.
Okay.
I know you mentioned iPad, but it's also fine if we just do it on notebook paper and scan it with our phones and turn it in, right? Because I
Yeah,
know
that's
that's how it would be in
perfect.
homework.
Yeah, that's perfectly fine too.
All right.
Yeah, definitely. Perfectly fine. Okay, I know that this is not, it's a lot easier doing things in person and I understand, the circumstances. And so, we'll try to do the best job we can and there might be some hiccups, but we'll deal with them. Okay. Other questions? Okay, so like I said, I will actually send you written notes or instructions on this. A lot of it will be the same as what I presented today. Um, but I just wanted to give you some ideas and not just leave you completely in the dark about the final exam. The actual final exam will basically be similar to the midterm, except it will just be twice as long. Okay. All right, other questions? All right. Okay, so let's go back to least squares. So let me give you a quick summary of least squares. All right, so remember what least squares actually does. So if you have a system of equations, ax equals b, this could be inconsistent. So what you'd like to do is you'd like to find the best possible solution. So the idea is to find the best possible solutions. And these are called the least square solutions. And the reason why it's called the least squares is that you're actually minimizing distances. So you take the error, and that's the length of ax minus b, and you want to minimize this. Right. So here's a picture. So you can have your column space of A look like this. And, the B, maybe your AX equals B may be inconsistent. So you may have a vector which is not in the column space. And the idea is we just want to find the vector in the column space and the AX, which actually minimizes this distance. Okay. And it's obtained by just basically projecting onto the column space in an orthogonal way. Now, last time we actually had a solution given. So, so first of all, generally, this is sort of the general solution. And the general solution, X has to satisfy A transpose A times X is equal to A transpose B. Okay, so that's what has to happen in order to minimize the error. Now, if A has linearly independent columns, you can actually invert the matrix, A transpose A. So if A, darn it. So A has linearly independent columns, then A transpose A is invertible. Okay, we saw that last time. And X here is going to be equal to A transpose A inverse A transpose B. And if you look at the projection, so the point inside the column space, which is closest to B, this is given by A transpose A inverse A transpose B. Okay, so these are two important equations to learn. Okay, any questions so far on this? So this is another term for this is called a linear model. So this is called darn, let me just erase this. Okay, so this is called a linear model. And your B here is equal to AX plus E, and E is the error. So this is the error, or what we call the residual term. All right, so later on, we'll actually do examples of this, but we're sort of in the midst of doing an example involving data fitting. And so I'd like to go back to the example and sort of finish it off with an actual concrete application. Okay, so we were looking at least squares. Fitting of data. All right. Okay, so here's the idea. So I have a plot and I have a bunch of points. So I have all these points around here and they're scattered all over the place, you know, and what I'd like to do is I would like to actually find the line which minimizes the distance between the points. Okay. So I want to find this line, and this line is R is equal to C plus DT. Okay. And last time what we did was we analyzed this, and so let me just kind of give you the summary. So this was the summary. And so it basically said the following. So given points T1, B1 up to TM, BM, the straight line that minimizes the distance is given by, I'll call it C plus DT, and where we have M, and then we have the summation of the TJs, and then we have the summation of the TJs over here, and the summation of the TJ squareds, and then C and D here have to be equal to the summation of the B's and the summation of the BI's times the TI's. Okay, so this left-hand side is A transpose A, and the right-hand side is B. A transpose B. Let me just write that out. So the way you should think about this is, write it in red here. So this part here was A transpose A, and this was A transpose B. Okay, so let me actually do an example for you where you actually can find C and D. All right, so let's do an example. Okay, so a spring was stretched on a rack to lengths of let's see, 5 feet, 6 feet, and 7 feet. Okay, under forces of let's see, F equals 1, 2, and 3 tons. Okay. So assuming Hooke's law, so here L is equal to the length, L is the length, okay? That's equal to A plus B times F. Find the best fit of data by least squares. Okay. So, you should just compare it to our little setup over here in the summary. So first of all, Hooke's law, it sort of gives something in terms of the length of the spring in terms of a linear sort of relation between F and also L. And so what you would like to do is we'd like to find out what A and B will be. So the L's that we have are given by 5, 6, and 7 here, and the F's given by 1, 2, and 3. So let's sort of identify these things. So I don't know, let me put it in blue here. Okay. All right, so the C and the D turn out to be just the A and the B, right? So this is the part C over here, and this is the part D that we're looking for. And then the T will correspond to the F, and then the R will correspond, or the B's will correspond to the L. Okay. So we should set this up so that, we have the T's coming first and then the B's coming after that. And then we can just apply the ideas. Okay. All right, so let's do that. Let me go back to this pen. All right, so let me just draw a little table here. Okay, so the T's are the F's. So the point's the F, and the B's are the L's. So this is like TB here, okay? All right, so at force 1 ton, I was able to stretch the spring 5 feet, okay? At 2 tons, we're able to stretch the spring 6 feet, and at 3 tons, we have 7 feet, okay? So the points that we have in question are 1, 5, 2, 6, and 3, 7. Okay, is everyone all right with that so far? All right. So so now we just have to apply this thing over here where we have to determine all these values and then we just solve. Okay. All right. So hopefully I can leave enough room up here. So let's see what we can do. So let me write it down here. Okay, so I think everything fits in. All right, so what's M going to be? How many points do we have?
3.
3? Okay, so what's the sum of the T's in our situation?
6.
6, good. And we have 6 over here. How about the sum of the T squareds? 1 squared plus 2 squared plus 3 squared. What do we get?
14.
14, good. Okay, sum of the BI's, that's going to be 5 plus 6 plus 7, that's 18. And then you take the inner product between the F's and the L's, right? So I have 5 plus 12 plus 21. So I get 38. Okay, everyone understand how we did that? So we just took this data and we just plugged it in to this formula up here. Okay, now we can actually solve for the A and the B. Okay, so we need to invert this matrix. So then AB, okay, so it's 1 over the determinant. That's what, 42 minus 12. 42 minus 36. That's going to be 6. Okay, so the A and the D switch, and I have to negate these two, right? And I get 18 and 38, sorry. And when you do that, I believe you get, I get 4-1 at the end. Okay, so you can do the arithmetic. Okay, so you can just do the arithmetic and you get 4 and 1, right? Okay, so I get L here. It's going to be equal to, what is A? A is 4 plus F. Okay, so that's the line that best fits the data. All right, any questions on this? Yes, no? All right, now someone asked last time about whether you can actually do things, instead of trying to best fit things via lines, whether you can best fit things using polynomials, or quadratics or cubics. And the answer is yes. And so let me show you how to figure out more general linear models. So this is more. All right. Now, what I'm going to do first is I'm going to sort of give you sort of the most general one, and then we'll specialize it. So the curve that you want to look at, trying to fit. So before it was a line, now it's some sort of curve, right? So it's B0 and some function. It could be in like two variables, U and V, plus B1 times another function in terms of U and V, plus BT times some function in terms of maybe two variables, U and V, okay? And U and V are independent variables. Okay, so what you do is you have these functions in terms of U and V, and then you just plug in a bunch of points, and then you want to find the betas. Okay, so the idea is you plug in points, and you want to find, you move this up a little bit. You want to find the beta J's. Okay. All right. So let's do an example where we actually try to fit a quadratic. So let's do an example. And you'll see the ideas are basically just the same. All right. So, so here's the idea. So our y here is just going to be equal to beta 1 x plus beta 2 x squared. Okay, so x and y are the variables, And I want to plug in points X and Y and then see what equations we actually get in terms of beta 1 and beta 2. All right. Okay, so we have 5 points. So we have 5 points. So we have x1 and x1 and y1, and that's equal to 1 and 1.8. There's a comma there. x2, y2 is going to be equal to 2, comma 2.7. And x3, y3 is going to be 3 and 3.4. And x4, y4 will be equal to 4 and 3.8. And finally, x5, y5. So there are 5 points. That's going to be 5 and 3.9. Okay, so these are the given points. All right. So when you do that, we have all these equations. So your equations, I'm not going to put the numbers in yet. So the equations are given by the following. So you have like yj is equal to beta 1 xj plus beta 2 xj squared, and you have these equations 1, 2, 3, 4, and 5. Okay, so you have these 5 equations. All right. Now, what we can do is we can sort of write this in vector form. So I can write the y's over here, y1, y2, y3, y4, and y5. Okay. So what we can do is we can sort of write this as x1 squared times beta 1 and beta 2. Okay, remember we want to find beta 1 and beta 2, and we get this linear system. So then we have x2 squared, x3 squared, x4 squared, x5, and x5 squared. Okay, any questions on how we got this? All right, so now let's plug in the numbers. So we plug in the numbers. All right, so I'm just gonna put the y's over here, and I get 1.8, I get 2.7, I get 3.4, I get 3.8, and I get 3.9. Okay. And then I'm just going to square. So remember what the x's were. The x's were 1, 2, 3, 4, and 5. Okay. So I have 1, 2, 3, 4, and 5 over here, and I take their squares: 1, 4, 9, 16, and 25. Beta 1, beta 2. Okay. All right. So this is a linear system of equations, right? So let me just label this. Let's change that to red. So what's our A here? Here's our A, here's our X, and here's our B. Okay, so this is a linear system. It's probably not consistent, but we can actually solve this now by least squares. Okay, so even though at the beginning your functions are not linear, you can actually put this in to actually get sort of a linear approximation in some sense. So that's what we're doing here. We're just sort of, taking a bunch of points and we're sort of just finding the best possible fit of those points using this minimization of the distance. Okay, questions yet? All right,
Oh, I had like a question.
Sure.
So does this approximation still work even if like if it's consistent? Like would
Yeah.
it just give us the exact line then?
it would actually give you the, exact line.
Okay,
I
gotcha.
mean, if all the points lied on a line, you would get the line.
Mm-hmm.
Okay. All right. Okay, so now we want to solve by least squares. Now we can actually solve for beta 1 and beta 2. So we can. So the question is, will the solution be unique? And the answer is yes, because if you look at A, what can you say about the columns of A?
Linearly independent.
Right, they're linearly independent. Right, good. So the columns of A are linearly independent. So X is going to be equal to A transpose A inverse times B. Okay, so we just have to find out what A transpose A is. So let's figure that out. So A transpose A. Okay, so 1, 2, 3, 4, 5. 1, 4, 9, 16, 25. Okay, 1, 2, 3, 4, 5. 1, 4, 9, 16, 25. Okay, so you can do the arithmetic and I'll give you the answer. So the answer is 15 and then 225 and another 225 and 979. Okay, any questions on this so far? All right. Okay, so now I have to apply it to B. So X is going to be equal to, I have to take the inverse. Right, so you have to take the inverse of this thing. All right, so let me just write it this way. So you have to do some more work, but I'll let you do this at home if you want. Okay, so let's do this here. So you have to take the inverse. So 1, 15, 225, 225, 979. And then you have to take the inverse of this. And then you have to apply this to the B vector. And what was the B vector over here? Okay. 1.8, 2.7, 3.4. Okay. 3.8, 3.9. All right. So that's the B vector there. Okay. All right. So you find the inverse of this matrix and then you do the matrix multiplication on B. And the final answer turns out to be like 1.76 and 0.20. Okay, so that actually figures out, so this is beta 1 and beta 2. So these are the coefficients that you get for the quadratic which best fits the data. All right. Okay, any questions on this?
I have a quick question.
Sure.
So we take the A transpose to minimize the equation because it basically dot products the A matrices. And that gives you the orthogonal square, I'm assuming here,
Well,
of the distance.
it goes back to our analysis at the beginning. All right. So what what this basically says is that you have to have, you look at this equation here, and if you take A transpose, that's A transpose B minus B equals 0, right? So this equation you sort of write in this way. And the point is that the vector AX minus B has to be orthogonal to the column space of A. So that means it's in the null space of A transpose. So that's what we did last time. So because it's in the null space of A transpose, we can get this equation. And that's what allows us to actually say that that's the best possible solution. So you have to go back to what we did in last class.
Okay, thank you.
Does that make sense?
Yes.
Okay. Other questions? Okay. Let's see. Wondering if I have a little time. And so let me kind of give you another, I'm just going to give you, this is very quick. I'm not going to put in all the details of this just because I don't want to get through it. But it turns out that the least square solution may not be unique. It depends if the columns of A are not linearly independent, then you may not have uniqueness. So if the least squares, or sorry. Okay. If the columns of A are not linearly independent, then it turns out the least square solution may not be unique. Okay, there could be like, a number of them. It could be an entire line of solutions. So let me give you an example where this happens. Let A, B, and C be distinct numbers. Okay. And let's say we have the following equations: x minus 2y plus 5z is equal to A. X minus 2y plus 5z is equal to B. So you got these parallel planes. X minus 2y plus 5z is equal to C. Okay, so certainly not consistent because we got three parallel planes, so there's no intersection. All right, so what is A going to be? Well, when you write this out, so then you get 1 minus 2, 5, 1 minus 2, 5, 1 minus 2, 5. And this is your A, and this is your B here. Okay, and your columns are not linearly independent. So columns of A are not linearly independent. Okay. So you could see that you're going to have you could potentially have lots and lots of solutions. So let's go through the least squares analysis. So All right, so if I take A transpose A, I'll just give you the answer. Okay, so it's 3 minus 6, 15, minus 6, 12, minus 30, and 15, minus 30, and 75. Okay, so notice that each row is a multiple of the first row. All right, so it's not invertible because your rank is 1. Okay, and A transpose B in this case is just going to be A plus C, and then minus 2 A plus B plus C, and then 5 times A plus B plus C. All right. So when you look at A transpose A times X is equal to A transpose B, then you do not have a unique solution. Okay. So the solution set, when you apply Gaussian elimination, is X, Y, and Z. And that turns out to be equal to, that's interesting. It's just going to be, oh, I see. Okay, so it's going to be A plus B plus C over 3, and I have 2 zeros. Okay, so it's not a homogeneous system of equations. This is the particular solution over here. And then plus S, so there are 2 free variables, S times 0, 2, 0. And then the other free variables is T, and that's 0, 0, and I have a minus 5. Okay, so you get multiple solutions. So the solution is not unique. Okay, so if you want a unique solution, it's very important to have, let's say, the columns of A being linearly independent. Okay, are there any questions on this example? Okay, so I've actually finished the subject matter for the entire course, so we can sort of congratulate ourselves. So on Monday, I will start in on a review. I'll probably review pretty hard on Monday and Tuesday, hopefully leave more Wednesday open for questions. Okay, or just going over specific questions about the material. All right. So that's kind of the plan for next week. So there will be no new material on Monday, Tuesday, and Wednesday. Okay. Questions?
Is our
Okay.
class, oh, sorry, is our class the same time on Tuesday?
Yes, it's a Tuesday is a Friday schedule.
Okay, gotcha.
So I've set things up already in Zoom for the same time
Okay,
on
thank
Monday,
you.
Tuesday, and Wednesday. Okay. Other questions? Okay, so if not, I wish you a happy and safe weekend. So take it easy.
Thank you.
All right, bye.